Let's start our talk about induction by looking at some statements that are provable by induction. So I put some quotes around this because I consider this a statement, and we'll call it P of n, and n is some natural numbers. We say that this is always true for n is integers or natural numbers. Usually they're natural numbers. Sometimes we got to dip into the integers, like maybe 0 or some negative ones, but there's always going to be a least element in the set of n. So the sum of the first n natural numbers is n plus 1 over 2. This is not really an equation. Well, you can write it as an equation, but it's a statement, and I think that this is what throws off a lot of people about induction. You're not proving expressions or formulas necessarily. You're proving statements, and here we can write it as a formula, but I'll show you some induction statements that really can't be written as a simple formula. Here's another one, a very famous one. Sum of the first n odd natural numbers is n squared. So that's another statement that can be proved by induction. Okay, so when we look at these two, it's about the sums of numbers or things, expressions involving natural numbers. We tend to think that this is all that induction is good for, proving things about sums of integers. And I think that that is a common attitude I see in the students. They don't see induction as having a very wide applicability to things beyond that. But let's look at some induction statements that are really oddball and really out there compared to these two familiar ones. Well, here's one. With only $3 bills and $5 bills, I can make any dollar amount greater than or equal to $8. Well, when was the last time you saw a $3 bill? But actually, this is true for any dollar amount greater than or equal to 8. For example, 8 is made from a 3 and a 5, 9 is made from 3 3s, and so on. And we can prove that this is true for all n greater than 8. Now, this is a very oddball induction statement. It doesn't look anything like the previous two. It's not sums of numbers, but this is something we can prove with induction. I'm going to do this one, but in the next induction video. Here's a good one. For all natural numbers n, cos x plus I sine x power n is cos nx plus I sine nx. Now, this is a very famous formula. I think it's called De Moivre's formula. Well, we could prove that by induction. And here's another one. AmGm is true. The arithmetic geometric mean inequality is true. Well, where's n here? Well, we have to expand this a little bit. Okay, so AmGm is this, the nth root of a1, a2, up to an is less than or equal to a1 plus a2 plus dot 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 an over n, where aj is greater than 0, positive a's, and let's take n as a natural number. So for all natural numbers, and this condition on aj, AmGm is true. So it does depend on n. And this is a very interesting statement. It's not a sum of numbers, really. You're saying, well, it's not a sum of integers. You're saying that this inequality is true for any of these n, any n here, choice of a root n here and an n here. So actually, I've proved this in 2 videos previously. So I will leave the links to this in the description box. Here we have a very pretty statement. The sum of the cubes of 3 consecutive natural numbers is divisible by 9. And this is true for any n. Okay, and well, we're beginning with n here. 3 consecutive naturals. Okay, so n plus 1, n plus 2. Okay, well, and that's divisible by 9. So that's a really beautiful, really pretty thing. Let's try to write this different way. 9 divides n cubed plus n plus 1 cubed plus n plus 2 cubed. Yes, we are going to prove this in a future video. I have a different one planned for you in this video that's really off the wall. Okay, it has to do with graph theory, and someone was asking me about graph theory recently, so it got me kind of interested, and so I found some way to introduce graph theory in this talk about induction. This here is the central concept of induction, and this has to be perfectly clear in your mind before you can start using induction effectively. So we read this like this: if pk, then pk plus 1. So if pk is true, then pk plus 1 is true. So notice that I am not saying that pk is true. I'm not saying that. I'm saying that if it is true, then the next one, pk plus 1, is true. Okay, that's the critical distinction here. I'm not saying pk is true. I'm saying that if this is true, then this is true. Okay, so I'll show you that this acts like a little machine that does our proof for us. Watch. Here I have lined up all my statements. P1, P2. Oh, I have 2 P2s. That should be a 3 here. P3. There, that's better. Okay, so if pk is true, then pk plus 1. So I can draw a line like this, an arrow from here to here. So if I know this one is true, then the next one is going to be true. However, I have a problem. I don't know that pk is true. I do not know this. All I know is that if it's true, then the next one is true. I don't actually know that it is true, so I'm not sure. But if we begin somewhere, let's say the simplest case usually is the first one. Let's say we are able to prove this. So let's say this is true, proved, okay, and we know it's true. We know true. So let's say we are able to do this proof some other way. We can prove the truth of P1. Well, now I can apply this proving machine here, this here, and I can get the next one. Bang. Now that I know this one is true, I apply pk implies pk plus 1. Well, k here is 1, so I know this one is true. Done. And now I apply this machine again, and I get the next one. The next one is true. Bang. I got it. And you keep going. Finally, I know that this is true because the machine has gone all along the line of natural numbers. I'm at pk now. I know it's true because I know the first one is true. Everything depends on the first one. All right. So now that we know the first one is true, we're all the way up here. We know this one is true. Now we know this one is true, and the machine does all the work for us now, goes off to infinity, all the way to Pn. Pn is now true, this one true, and then the next one we know is true because in each step we are applying pk implies pk plus 1. So what did we do here? Well, we proved two things. We proved one. We proved P1. This is called the base case. And 2, we needed this, the machine that moves along all the natural numbers. We needed to prove this. We assumed that this is true, so we assume we proved it somewhere. pk implies pk plus 1. Okay, so that's it. That's how induction works. If you want to prove something is true for all n, then you prove two things. You prove this, the base case, and then you prove this. This is the induction step. It's like a machine that steps through the numbers and proves them one by one. It proves P for each one by one, and it keeps going and going and going. All you have to do is get it started. Here, we were not able to get it started. All we knew was that if this is true, then this is true. So we can apply it, but we don't know that this is true, PK. We're not sure. We don't know. So we can't get the machine going. But if we can start it by proving P1 is true, well, then the machine has something to latch on to. It starts here and it keeps going and going and going and so on and so on and so on and on and on and on. Okay, so that's how induction works. We need to prove the base case. We need to prove the induction step. And this, if we can do these two, this and this, then, therefore, or with those two, Pn is true for all natural numbers, n in natural numbers with n greater than or equal to 1. Well, okay, natural numbers are greater than or equal to 1, but sometimes the base case is not 1, sometimes it's 2. Sometimes it's easier to prove this one than it is that one, or sometimes the first one, P1, doesn't apply. We have to start at P2. So just keep in mind the base case doesn't have to be 1. It could be some other integer. As long as it's the base case, we're okay. So I want to point out one more thing, that nowhere do we prove PK directly. We don't do that because it might be very hard to prove PK directly. We prove P1 directly. This is direct proof. This might be very easy. Usually this is very easy, the base case. And this is usually not so bad. It could be pretty hard, but it's usually doable. But this might be very hard. Could be very hard. And that's why you want to use induction on these problems. So we're not proving PK directly. We only assume that if it is true, then this is true. We have to prove this implication. This does not prove that PK is true. This proves that if PK is true, then this PK plus 1 is true. This kind of implication, I think, is another point that confuses people who are learning how to use induction, because they're used to trying to prove a statement like PK. You know, they want a concrete statement to latch onto and they want to prove that. They don't like the idea of proving this kind of implication because they say, well, what is that? If PK is true, then PK plus 1 is true. You know, that's something, it's an extra level of abstraction beyond proving PK that I think could be confusing. So the best way to get over this confusion about how to use this, how to prove this, and how to use this is to do a lot of examples. Okay, but before we do that, we're going to prove that induction actually is justified and it works mathematically. Is there a way to justify induction mathematically, rigorously? Is there a way to prove it? That sounds a bit odd, like we're asking to prove a method of proof. Can you prove that proof by induction works? But actually, yes, we can prove it. And one way to do it is to use proof by contradiction, which is like the sword of Excalibur on really hard problems or confusing problems. Just use proof by contradiction. It might work. So we will be able to justify induction. So let's start. We'll start by saying that proof by contradiction doesn't work, and then we'll derive a contradiction. So we assume induction doesn't work. What does that mean when we say induction doesn't work? Well, it means this. We have these two. These two are okay. They're established. They're proved. But Pn is not always true. Okay, so this is the way to say that induction doesn't work. The two required pieces of the proof by induction, we have both of them, but Pn is not always true. Still, it fails. And there has to be a number for which it fails. And we take m, let's say, to be the smallest number. Smallest integer for which Pm fails. There's got to be a first one for which this fails. There may be many of them, but there has to be a first one. So that's what I mean by induction doesn't work. We have the prerequisites, but one of them somewhere fails, and Pm is the first place where Pm fails. We can immediately see something about m. First of all, m has to be bigger than 1, because if m is 1, well, P1 doesn't fail. We've proved that to be true. So we know that m has to be bigger than 1. So m minus 1 is clearly defined. It's not 0, okay? If it was 0, then it's below our base case and outside the range where our induction is applicable. But it's greater than 0. So it's within the range of 1, 2, 3, and so on. And this is where our induction applies. Yes, our induction applies in this case because our base case is 1. So everything is clearly defined. So Pm fails. However, Pm minus 1, this must be true because Pm, well, m is the first place where P fails. So before m, all of the p's must be true. All of the statements must be true for the numbers smaller than m down to the base case. But we have already proven that pk implies pk plus 1. So if this is true, then this must be true also. But this is a contradiction. It's a contradiction because we assumed that Pm fails. All right, so there is a contradiction here. Therefore, no such m exists, and Pn is true for all n greater than or equal to 1. Beautiful proof. I think you should remember this proof. It's beautiful because this proof really goes to the heart of what induction is. And if you understand this justification of it, if you understand how this proof works, then you will understand exactly how induction works. As an example of induction, I've tried to choose something that's really oddballish, something that's not sums of numbers like you may have seen before. This one has to do with connected planar graphs. Here's a graph. This graph's actually planar, but it's not connected. Okay. This one is connected. I'm sure you can see the difference. This is two disjoint pieces, but this one has an edge joining the two. So, intuitively you understand now what is connected. Now we have to talk about what is planar. This graph here is planar. None of the edges cross each other. It can be drawn without crossing any edges. However, this graph is not planar because there's no way I can draw this without crossing edges somewhere. So for example, if I erase this edge here and I try to draw it outside, that's fine. And then if I try the same with the other one, I'll end up crossing lines again. So there's no way to do it without crossing the edges. I must point out here that there's no node, there's no vertex there in the middle where the edges cross. So as an exercise, you can try to draw this graph without crossing the edges and you'll convince yourself that it's impossible. Okay, so let's look at a very simple graph, planar connected graph. This is a really simple one. How many vertices do we have? Well, we have 3. 1, 2, 3. How many edges do we have? We have 3. And how many faces do we have? Well, there are 2 faces. I'll show you. One is inside, but the face outside is like a big ocean that the graph lives in. that's another face. So we can form this combination, Euler's characteristic, vertices plus faces minus edges. And let's try to work this out. So vertices here is 3, faces is 2, minus edges is minus 3, and we have 2. That's very interesting. That's 2. Now let's try it for another graph. Okay, something like this. All right, like this. You can draw graphs at home and add these things up. It's all very fun and interesting. How many vertices here? There's 4. How many edges here? There are 1, 2, 3, 4, 5, 6. 6 edges. How many faces? There's, okay, be careful. 1, 2, 3. But then there's the big ocean outside, and that's 4. So let's see, vertices. Let's calculate phi, the Euler characteristic. Vertices plus faces minus edges. That's 4 plus 4 faces minus 6 edges. Wow, it works out to 2. Wow. Okay, so we're going to prove that phi is 2 always. Okay, and this we're going to do by induction. There's other ways to prove this, but I'm going to use induction. The induction proof is really cool. And this is a great example of something that's completely not like adding up sums, but it can be done by induction. So the main idea of this proof is that we're going to build graphs. So we're going to start with a graph that I'm going to call G0. And G0 is really simple. It's just a dot. It's one vertex, no edges, okay, and that's G0. So we're going to then do graph operations that will build up any planar connected graph. The graph operations take a connected planar graph and build up the next biggest one. All right, so here's one way. Let's say we have a connected planar graph. Okay, we have, it may be connected to a lot of edges and vertices, but between 2 of the vertices, what I can do is I can add another vertex. So I can break that edge into 2 edges and add another vertex. So let's calculate the change in the number of vertices. Well, that's +1 because we added a vertex. And what is the change in the number of faces? Well, that's no change here in this case. And what is the change of edges? That's +1. We added an extra edge. Now look here, suppose, it's connected, so maybe it's connected this way, maybe connected this way. So you have these 2 faces here. There may be many more faces, who knows. But the thing is that this did not change those facts. Adding this vertex did not change anything. It did not add an extra face. There's still a face on this side, still a face on this side, if there are faces. It can be connected even though, for example, there's no connection this way. So this is one way to do it. And then now we can calculate the change in phi. So whatever phi was here, I don't know, but phi here is going to, I have to add these things up. This plus this minus that gives me 0. So the change in phi is 0. I don't know what phi is here. Okay, and I don't know what phi is here, but I know that there was no change in doing this operation. So that's very interesting. There are 3 more of these basic graph operations that we can do for building our graph. Operation B. All right, so now here I've got 2 vertices, and these have to actually be connected. Otherwise, it's not a connected planar graph. It's disconnected. So somewhere out there, they're connected. This may be very complex connections, but they are connected eventually. Now, what I'm going to do is take these 2 vertices and just draw draw a edge between them. So I have this set up, this with eventual connection. I draw in yellow like this, and I add an edge in between these two. So what changed? Well, the number of vertices didn't change. The number of faces, yeah, that did change because I had one big face here, but now I have two faces here. Okay, so in fact, this went up by 1. And the number of edges, this changed by +1. So what is delta phi? Well, when I add this up, v plus f minus e, that's 0. So whatever phi was here, it is the same phi here. This did not change. That's very interesting, very surprising, very amazing. Okay, so let's go to the next graph building operation. I have just one vertex here. It may be connected to some very complex planar graph out there, but it ends over here in a vertex. And I create what they call a self loop. This is another way to build a graph. I'm building a connected planar graph from a connected planar graph. So this is another way to do it. So what changed here? Change in vertices, 0. What about the change in faces? Well, yeah, I have added this extra face inside that bubble, so that's a +1. Change in edges, that is also a +1. So if we do vertices plus faces minus edges, we can calculate change in phi, that's 0. So whatever phi was here, there's no change. It's going to be the same here. And finally, we've got one more graph building operation. We start off with a vertex here connected to some big graph like in C. But here what we do is we add an edge and a node, an edge and a vertex. This actually is different. It produces something different from the others. You'll see that if you don't add this particular graph building operation, there are types of graphs you won't be able to build. You can try that yourself. And now let's calculate the change. Change in vertices is +1. Change in faces is nothing. There's no change. We didn't add a face by doing this. Edges, we added an edge. Delta phi here is again 0. V minus f. V plus f minus e is 0. So whatever it started off here as phi, it's the same phi here. Now let me show you some illegal operations. For example, this graph building operation here, suppose I have a node like this or a vertex, and I build something like this, and I draw that. Why is that illegal? Well, this is not a graph. Not a graph. Because a graph must have an edge between vertices. You can't have an edge going to nowhere like that. It has to end in a vertex. And another thing that we can't do is like this. We can't start with a graph like this that has a vertex floating out there and connect it up with an edge. But these are valid graphs, but the problem is that this one is not connected. So if it's not connected, then it's not a connected planar graph, and we're building from one connected planar graph to another. So this operation is not allowed, and some operation like this is impossible. This can't happen here. If we want to add a node or a vertex outside of the main body like that, we have to use step D here. We have to use this. We have to add the vertex and an edge at the same time. See, that's why we need graph building operation D. So now let's do our induction. Let's do the base case. So the base case is actually going to be P0. Here's an example of where I'm not starting at 1, I'm starting at 0. And P0 is the graph G0, which is just one vertex. So let's calculate phi for one vertex. This is connected planar graph. It's just a very trivial one. So this is number of vertices is 1. A number of edges or a number of faces is 1. Remember, the big ocean is one face. And then finally, the number of edges is 0. So phi is vertices plus faces minus edges. That's 2. So the base case is true. Phi is 2 for the base case. And 2, let's assume that it's true for graph that's pk, where the graph has been built from G0 by k operations. So I did k of these A, B, C, D operations in any order. It doesn't matter how you do them. You're always going to get a connected planar graph. So I did k steps of building a graph, and I have proven this thing here. I have assumed that this is true. Well, I haven't proven it. I have assumed that this is true, and we want to show that pk implies pk plus 1. Well, what does this mean that I have assumed that this is true? It means that for my graph, phi is 2. But we showed that for all of the graph operations, A, B, C, D, the change in phi is 0. And so pk plus 1 is true, because for the k plus 1 step graph, let's see if I can write that clearly. Phi must also be 2. Okay, and we know that it starts off at 2. So this walks down the line like I showed you. Like I showed you, the machine starts here. We know phi is 2 here. And because we have proven this, that if this is true, then this is true. This has to be true because the change in phi in this step is 0. So it doesn't change. If phi is 2 here, it's 2 there. So then this must be true. And then the machine walks. pk implies pk plus 1. It keeps walking along and keeps going and going and going. And it does all of the proof of every step for us. And so therefore, is true for all graphs. Phi is 2 for all connected planar graphs. Okay, so that's quite an amazing proof. Probably you have to go through it a couple of times to really convince yourself. I hope I made it clear. I guess there are ways I could try harder to make it clearer, but we'll see. I'll maybe try doing this proof again in the future. But look, if you don't understand how induction works, or if it's foggy, don't worry too much, because in the next video on induction, I will do a whole bunch of examples which will give you a lot of practice and a lot of food for thought. So don't panic. Okay. And I will see you next time. But before I see you next time, click like and subscribe. And I will see you next time.